Thomas had been lied to for most of his adult life, not maliciously, not by any single person, but by an entire industry that had quietly decided sometime in the post-war decades that a house had to look a certain way. Rectangular, peaked roof, stick frame, load-bearing walls every 12 feet, and that any deviation from that template was either a mistake or a compromise. The construction industry had built an entire economy around that template. Suppliers, codes, financing, insurance, contractor licensing, architectural norms, all of it optimized for the rectangle. And for 40 years, Thomas had accepted that template the same way everyone else did, without ever asking the single question that changes everything. What if the rectangle is the problem? That question led him somewhere most builders would never look. It led him to a shape that is almost 80 years old, that was used to house military aircraft and store ammunition in the Pacific Theater, that you have almost certainly driven past 100 times without giving it a second thought. It led him to the Quonset Arch. And 3 years after breaking ground on a remote 11-acre parcel in interior Alaska, Thomas was standing outside a 1,500-square-foot barndominium he had built for $60,000 flat, materials, labor, and every single off-grid system included, thinking about how completely, systematically wrong everything he'd been told about building had been. The sign next to him said it plainly: the $60,000 Quonset Barndominium. Complete project cost, $60,000. He had put it there on purpose. He wanted every person who drove down that gravel road to see the number before they saw anything else, because the number was a point. In Alaska, where construction costs run 2 to 3 times the national average, and where a modest stick-frame home in a rural area eats $300,000, before you hang a single door, $60,000 for a fully functional off-grid dwelling is not just a bargain. It is an indictment of every assumption the construction industry wants you to keep making. Here is what Thomas figured out that the industry doesn't want you to think about too carefully. The rectangle is not the most efficient shape for a building in a cold climate. It is the most profitable shape for the people who build them. Every corner of a rectangular structure is a cold bridge, a place where exterior temperature migrates directly through material into your interior, bypassing your insulation, raising your heating load, costing you money every single hour of a subarctic winter. Every joint in a stick frame wall is a potential failure point, a place where water can enter, where air can leak, where the structure negotiates with physics instead of simply winning the argument. Every ridge beam, every rafter, every double header over a window opening exists because the rectangle requires constant reinforcement against the loads it was never designed to carry efficiently. Alaska applies those loads without apology. Snow that weighs more than 100 pounds per square foot in a heavy year. Wind that doesn't read load tables. Ground that freezes 6 feet down, that heaves and settles on its own schedule, that has crack-poured concrete foundations that took 3 months and $40,000 to put in place. The rectangle, built by lower 48 logic and financed by lower 48 assumptions, meets Alaska and begins losing immediately. Thomas had watched it happen to people smarter and better funded than himself, more times than he could count. The Quonset Arch doesn't negotiate with Alaska, it simply redirects it. An arch is the most load-efficient structural form in engineering history. Civilizations have known this for more than 2,000 years. The Romans built aqueducts and amphitheaters with arch geometry that is still standing while every rectangular wooden structure from that era rotted away a millennium ago. Load applied to the crown of an arch doesn't concentrate at a failure point the way it does at the ridge of a peaked roof or the center of a horizontal span. It travels along the curve, converting downward force into compression that distributes evenly to the foundation. The steel handles it the same way a bridge handles vehicle weight, not by resisting at one point, but by spreading it across the entire structure. 3 feet of wet Alaskan snowpack on a traditional roof is a crisis. 3 feet of wet Alaskan snowpack on a Quonset arch is a Tuesday. Thomas sources kit from a manufacturer that still builds them the same way they were built in the 1940s. Galvanized corrugated steel panels that bolt together along the arch profile to form continuous self-supporting shell. A 30 by 50 foot kit, including all panels, hardware, anchor bolts, ridge cap, and assembly documentation, delivered this gravel road for $18,500. That was the starting point. That was his roof, his walls, his structural system, and his weather envelope in a single line item. No framing contractor. No lumber package that arrives incomplete and gets requoted halfway through project. No ridge beam engineered for a specific snow load by a structural engineer billing $180 an hour. $18,500. And the hardest structural problem in Alaskan construction was already solved. But here is where it gets interesting, and here is where the clear span advantage becomes something that goes far beyond just a roof. Because the Quonset arch is a complete self-supporting structure, it requires no interior load-bearing walls. None. The entire 1,500 square feet inside Thomas's building was open floor space from the moment the last arch panel was bolted in place. No columns, no shear walls, no structural elements dictating where you could and could not put a door. This is what clear span means, and it is a kind of freedom that conventional construction simply cannot offer at any price. You do not get to remove a load-bearing wall from a stick frame house because you change your mind about the layout. You do not get to reconfigure the floor plan after the framing inspection. In a clear span Quonset, the structural system doesn't care what happens inside it. The layout is entirely yours, entirely flexible, entirely reversible if your needs change. Thomas divided his 1,500 square feet into 3 zones and put them in an order that was determined entirely by thermal logic. The front third, the section nearest the timber frame entrance he'd built by hand from spruce felled on his own property, became the living area and kitchen. The wood stove sat here, on a stone hearth pad, throwing heat toward the rear of the building through the open plan. The windows cut into the arch face on the south-facing wall captured whatever low winter light Alaska offered and added passive solar gain that reduced the stove's daily load. The middle third held the bedroom, a bathroom with a composting toilet and gravity-fed shower, and a small mechanical workshop. The rear third was pure utility, the battery bank, the water tank, the deep storage. The thermal intelligence of that sequence is not an accident. Heat rises and migrates from high concentration toward low. By positioning the primary heat source at the front in the storage, where temperature mattered least, at the rear, Thomas created a natural thermal gradient that warmed every space in the order of its importance. The arch shape amplified this by minimizing surface area relative to interior volume. A rectangle has more exterior surface per cubic foot of interior space than any other shape. That surface is where your heat escapes. The arch, by eliminating the flat ceiling and the dead attic space above it and the cold bridging at every wall-to-ceiling corner, gives you less exterior surface per cubic foot of interior space than a rectangle of equivalent area. You are losing heat through less building envelope. That geometric fact is worth thousands of dollars per year in fuel you do not buy. Every smart Alaskan builder eventually learns that the real enemy in subarctic construction is not cold. It is moisture. Cold is predictable. You can insulate against cold. Moisture is a variable that destroys buildings, that rots structure, that corrodes steel from the inside, that turns a 10-year-old building into a demolition project. And the single biggest moisture threat in a cold building is condensation, warm interior air contacting a cold surface, giving up its water content, and letting that water freeze inside your wall assembly where you will never see it until damage is already done. This is where most Quonset builds go wrong, and Thomas had researched the failure modes obsessively before touching a tube of caulk. You cannot insulate a steel arch with fiberglass bats. There are no stud cavities to stuff them into, and even if there were, a bat-insulated assembly allows air movement that carries moisture toward the cold steel. The correct approach, the approach Thomas used, and the one that every serious cold-climate Quonset builder eventually arrives at, is closed-cell spray polyurethane foam applied directly to the interior steel surface. Closed-cell foam at 2 inches delivers approximately R13. More importantly, it delivers a Class 2 vapor retarder, meaning moisture from the interior cannot migrate toward the steel because the foam physically seals every square inch of the corrugated profile. Thomas applied it in 2 passes, a thin initial coat to fill the corrugation valleys and eliminate any air pockets where condensation could hide, then a full application bringing total depth to 3 inches in most areas and 4 inches at the arch base where ground-level cold bridging is most aggressive. Over the foam, he installed hat channel furring strips, thin steel channels that create a mechanical fastening surface, and over those he applied tongue-and-groove pine paneling he had milled from the spruce on his property. You need to understand what that interior looks like, because the image in your head right now is almost certainly wrong. People hear Quonset hut, and they picture a bare corrugated steel tube. What Thomas built was a room with a continuous curved pine ceiling that followed the arch profile from floor to floor. A ceiling that had no flat plane, number 90-degree corners, no the cheap suspended tile, or the generic drywall that characterizes everything built with a framing nailer and a production schedule. Light reflected off the curved surfaces differently than it does in a box. The acoustic character was unexpectedly warm. Multiple people walked through the timber frame entrance on separate occasions, looked up at the curved pine overhead, and asked Thomas which architect had designed the space. Every single time, he had to stop himself from laughing. The timber frame entrance was its own project inside the project. Thomas felled the spruce himself, debarked the logs by hand, rough milled them with a portable sawmill he had borrowed from a neighbor, and joined the posts and connecting beam with traditional mortise and tenon joinery. No metal fasteners in the primary connections, just geometry and compression, the same way timber framers have been building in cold climates for 600 years. The frame served three purposes simultaneously. First, it created a covered porch that functioned as a thermal airlock, a transition space between outside cold and interior warmth that reduced the thermal shock to the building every time the door opened. Second, it gave the building a human-scale front face, a visual identity that transformed the industrial arch into something that clearly said, someone lives here intentionally. Third, it provided mounting points for the outdoor lighting, the firewood rack, and the vintage refrigerator that Thomas used as passive cold storage through the 8 or 9 months per year, when outdoor temperatures made running a compressor redundant. The off-grid systems are where the $60,000 total becomes truly difficult for most people to believe, because the off-grid industry has a financial incentive to make systems seem more complex and more expensive than they need to be. Thomas had priced conventional off-grid solar installations before committing to his own approach. The quotes came back at $35,000 to $55,000 for a system designed to support standard American household electrical loads in an Alaskan climate. Those quotes were not dishonest. They were simply scoped to the wrong problem. The right problem is not, how do I replicate urban electrical consumption in a remote location? The right problem is, how small can I make my actual electrical need without sacrificing quality of life? And what is the minimum system that reliably covers that need? Thomas answered the second question before he ever spec'd a solar panel. He replaced every light in the building with LEDs drawing a fraction of incandescent wattage. He cooked on propane, eliminating the single largest electrical load in a modern kitchen. He heated water with a combination of propane and a thermosiphon solar collector he built himself from copper pipe and salvaged tempered glass. He used the outdoor temperature as a refrigerator for most of the year, keeping his compressor base cooling to summer months only. After all of that, his average daily electrical draw was 1.8 kilowatt hours. A 1,200-watt solar array, 4 panels, straightforward roof mount, with 4 lithium iron phosphate 100 amp-hour batteries, and a 2,000-watt pure sine wave inverter covered that load with buffer to spare. During the darkest 3 months of Alaskan winter, when solar input dropped below his daily draw, a small propane generator ran for 2 to 3 hours on overcast days to top off the bank. Complete electrical system cost $6,200. That number is not a misprint. $6,200, because the conservation work was done first and the supply system was built to match actual demand rather than assumed consumption. Water came from a hand-dug well at 22 feet, pumped by a 12-volt submersible to a 200-gallon insulated holding tank in the rear utility section. Gravity, the tank sitting 8 feet above the fixtures, provided adequate pressure for a shower and kitchen sink with no pressure pump required. The system froze in 2 locations during the first winter. Thomas added heat tape and additional rigid foam insulation around the vulnerable sections, and has not frozen in 3 winters since. Heating was wood from his own property, for cords cut, split, and stacked per summer. 2 to 3 cords burned per heating season. The surplus went to neighbors or stayed in the woodshed as a buffer. His annual heating fuel cost, beyond his own labor and saw maintenance, was effectively zero. The complete budget, which Thomas documented because he knew people would demand it, broke down this way. Quonset kit, $18,500. Foundation, perimeter grade beam with helical piers to 6 feet below frost line, $7,200. Spray foam insulation, contracted out for $1,100. Interior finish work, including paneling, flooring, windows, cabinetry built from birch plywood, all labor by Thomas, $8,400 in materials. Timber frame entrance, all labor by Thomas, $2,100 in hardware and milling. Plumbing rough and finish, $3,200. Complete electrical system, $6,200. Wood stove, chimney, and hearth, $2,800. Everything else, sealants, fasteners, vapor barriers, propane system, composting toilet, solar hot water collector, trim, deck materials, $7,500. Total, $60,000. 14 months. No debt. No contractor Thomas hadn't personally vetted. There are 3 things that number does not include, and Thomas was honest about all 3. It does not include the land, owned free for 9 years before breaking ground. It does not include the tools, accumulated over decades of working on his own property. And it does not include the knowledge, the reading, the failed experiments on smaller structures, the conversations with experienced builders that taught him what actually worked in this climate as opposed to what the textbook said should work. The knowledge is the part that cannot be purchased and cannot be rushed, and it is the reason Thomas told people who came to his door, drawn by the sign, to treat the $60,000 as a proof of concept rather than a replication template. What could be replicated, he said, was the thinking, the refusal to accept that a home had to be a rectangle. The willingness to look at an industrial form, a shape the construction industry had filed away as unglamorous and unsuitable for residential use, and ask what it was actually good at. The discipline to reduce consumption before specifying supply, to solve for heat loss before sizing the stove, to eliminate every unnecessary load before buying a single solar panel. The arch was the answer because Alaska was a question the rectangle had been failing to answer, expensively, for as long as people had been trying to build in the cold. Thomas stood in the January air with frost on his beard and looked at the building. He had not set out to build something beautiful. He had set out to stay warm and solvent in a place that made both of those things genuinely difficult. What he had built was the most honest structure he had ever seen. Every choice driven by necessity. Every detail responds to a real condition. Nothing added because convention expected it, and nothing left out because convention didn't understand why it was there. He picked up the whiskey from the top of the vintage refrigerator. It was his birthday. He was 51. The building was 3. Both of them, he thought, had figured out how to survive in Alaska. He went inside, pulled the timber frame door closed behind him, and let the wood stove do the rest.